general discussion about anomalies, right? So the type of things that we want to understand why do we want to have why do we want to have C equals 0, right? Or in other words, why do we want our wild symmetry to be anomaly free? Okay, so this is the same here as anomaly free wild symmetry. And so here, when we talk about anomalies, we have to distinguish two possibilities, right? So in quantum field theories, there are two types of symmetries. So symmetry in QFT. So what we can have global symmetries, and then we can have local or gauge symmetry. Okay, so global symmetries is something that helps you often guess the structure of correlation function. So it puts a constraint on your theory. And so if you have anomalies, if you say have some classical global symmetry and you find out that it's anomalous, then not a big deal. It simply tells you that what you thought were the constraints that will be they will be violated by quantum effects. Okay, so in principle, there is no problem in having anomalies.
Shouldn't global symmetry be actually unphysical? Because
no, it is physical. Actually, you have it wrong. So it's the other way around. I'll talk about this. So what is physical? Global symmetry is really a physical symmetry, right? No, global symmetry is a symmetry that I don't think of it as causal or causal. A global symmetry simply tells me a degeneracy, right? So if I have, for example, SU2 symmetry, and I say it's a global symmetry, and I have particles, and I know that SU2 is my global symmetry, that simply tells me that whatever particles I find must be in this SU2 multiples, right? So which tells me, you know, if I find that one member of a multiplet, it must be the case that I will have the right number of additional particles with the same mass and all the same other charges. So actually, global symmetries are physical symmetries. They are symmetries of the physical spectrum of your theory. But what I'm saying is that if it is anomalies, then it's not a big deal. That simply means that you don't have that symmetry in your full quantum spectrum. Something that I don't have time to talk, but something that those of you who will go ahead and continue studying quantum field theories and in more details, anomalies in global symmetries are often very useful. Okay, and the point is, this is known as, I'm going to just say the word and maybe just give you an idea roughly how it can be used. And so what I'm talking about is a so-called anomaly matching condition. Okay. So what can happen is that you start with a theory. It has some number of degrees of freedom. So usually you start with a QFT. So I have QFT defined with a UV, and it has some global symmetry, right? And what you find out, you compute quantum correction, and you find out that this quantum correction, this global symmetry is violated by quantum corrections. So the 'Hooft argument tells you, so you have a QFT in the UV and a QFT in the infrared. And as you go from the short distance properties in your theory to a long distance, a lot can change, right? So when we take non-abelian gauge series, so here we have asymptotic freedom, right? And here we have confinement, right? So here we cannot observe gluons, right? So what we observe mesons and baryons, right? So so there is a restructuring, complete restructuring in your theory. However, what 't Hooft showed is that if you have anomalies in global symmetries, then you compute anomaly in the UV, or you can compute anomaly after the theory completely restructured. And the point is that the anomaly must be the same. Okay, so global anomaly, anomaly violation. I'm not going to go into detail how exactly you quantify it. So those of you who are interested, well, this is very often people using supersymmetric gauge series, in particular gauge series, which as we know, which is infrared. There is confinement. So anomaly violation is the same, right? So what this tells you, this actually allows you to put constraints exactly what are these degrees of freedom. So here there is a complicated strong coupling dynamics, and you might don't know what it is. But very often, just by requiring that the global symmetry up here, when you have a nice weak coupling description, would match with anomalies at strong coupling, allow you to very often guess what the physics down here is. Okay, so anomalies in global symmetries is very useful, and in particular by matching, doing the 't Hooft anomaly matching condition, you can find what's known as a dual descriptions of the theory. Okay, so that's the notion of duality. So here you have a theory in terms of 1 degree of freedom, and here you have the theory described in terms of completely different degrees of freedom. And the point is that very often you can show that you guess correctly what is the dual description of the series once you match the 't Hooft anomalies. Okay? Now, we're going into a local symmetries, okay? So local or gauge symmetries. And gauge symmetry is exactly what I would call a non-physical in the language. So what I mean by that is that gauge transformation is redundancies in your description. Okay, so think of it this way. So you have a theory which has certain number of degrees of freedom, and then you have gauge transformation on top. So the physical degrees of freedom are the ones which you will obtain by dividing by gauge transformation. Okay, so that's exactly the philosophy that we did when we did a path integral, right? So in the path integral, so we identified the gauge invariant orbit, and then we integrated along the path that intersects each gauge invariant orbit only once. So what we did, pretty much in doing so, we are saying that, well, to go from this point to this point on a gauge slice, it's not physical. Okay, so it's simply a redundancy in your description. So is this clear? Now, once I said this, it must be immediately obvious to you how bad it is to have anomalies in local symmetries, even though those are gauge symmetries and they don't show up in the physical spectrum of the theory. Why is it bad to have anomalies in it? Well, the reason, can somebody tell me why? See what this gauge symmetry is doing, right? So originally you had a degree of freedom which were living on a plane, roughly. But if you say that those guys are gauge transformations, then you reduced your physical degrees of freedom living along the line, right? So what you did, you cut the number of physical degrees of freedom. You cut the number of physical degrees of freedom depends on what is your gauge symmetry, right? Because you have a big configuration space. So I don't know how to write it down. So configuration space, physical configuration space, physical space physical configuration space equals total configuration space divided by gauge symmetries, by gauge symmetry. Okay, so that's the way how you get the physical configuration space. So now, if you screwed up what you mean by gauge symmetry, which means that you screwed up in identifying what are your physical configuration space, which means that you misidentified the number of physical degrees of freedom. So it's not a surprise when I tell you that when you discover that your local symmetry has an anomaly, then the theory can lead to violation of unitarity, which is simply the point that you don't really know what are the degrees of freedom. That changes whether you include quantum corrections or not. Okay, so even though this local gauge symmetry, I'm saying it's unphysical, but because it is a redundancy in your description, it must be anomaly free. You cannot have anomalies in local gauge symmetries. Okay? Can never be anomaly free. Sorry. This has the opposite. It can never be anomalous. Sorry. So it can never be anomalous, right?
Or on the other hand, is it also if you keep the unitarity, then and different points in the configuration space?
Yeah,
the observers see different physics.
See, what you change this, right? So you are changing what you mean by, by your physical theory. So which would be the same as kind of going back and saying, look, you told me that that's your gauge symmetry, but it's not. It's like a smaller group or a subgroup. And so I get the right configuration space and build up my quantum mechanics on the correct physical configurations. You can do that, and that will be a fine thing to do. I'm just saying that if you will, insist that that's your gauge symmetry, but if it is anomalous, then you will have a problem. Okay? So now you can see that in the Polakov string, it was crucial for us. It was crucial for us to insist that Weyl symmetry was anomaly free because it was a gauge symmetry, right? So Weyl symmetry, Weyl transformation was something that we treated alongside with diffeomorphism transformations on the worldsheet, and we wanted to divide by those symmetries. So in Polakov, write it down. So in Polakov action, in Polakov string, Weyl transformation, we take it as gauge system, right? As gauge local. And that's why we had to insist that it's anomaly free. Okay, so is it clear? Is the logic clear so far, right? Okay, so then you might ask me, well, I don't care. It's kind of along the lines that, okay, so you misidentified the gauge symmetry, which simply means that you misidentified your different, what's your physical configuration space, and you say, I'm going to live with that. Okay, so what will happen? If you say you don't care, and Weyl is not gauge, anymore. Right. So all what it tells you is that when you construct a partition function for your string, right? So before it was a passive integral dx e to the minus sx, right? And so remember what we did? We divided by dphi times Weyl, right? Because we were thinking of it as a gauge symmetry. But now you're going to say, look, I'm going to look at my string theory such that the total central charge is not equal to 0. So I can no longer treat Weyl symmetry as being anomaly free, which means that I cannot divide by the volume of the Weyl symmetry transformation group, which simply means that I will just have an additional field that I will integrate over it, and I will just get a different type of a string series. Okay, so this will be not Polakov string. And so you would say, okay, fine. So I don't see so far any advantage to our physical world of a political string. So if you are telling me there is a different way, so let's go ahead and do that. And the problem here is that that's not quite right. So the political string is the one that is very beautiful and will lead to interesting physics. And wherever this one leads, I don't really know, but definitely it's not going to have the same consequences. So let's call this our string theory, right? And there is a political one. And so the only something right. Okay. So let me just mention why our is bad and political is good, right? So far, we assume that political string propagates in flat spacetime. So in Minkowski flat spacetime, right? E minus 1, comma 1. Right? That's an ambient spacetime in which our string propagates. But eventually, and this is something that we're going to discuss. We're going to discuss first scattering amplitudes in the string theory, and then propagation of the strings in curved spacetimes, right? So eventually, we want to study, and there will be a relation between scattering amplitudes and a coherent background in which the string propagates. So eventually, we want to study strings in curved spacetime, right? One of the reasons why we want to study strings in curved spacetime, something that we'll discuss we'll start discussing definitely today is, so remember in the spectrum of the string theory there is a graviton. So what I can think of is that as my string propagates, it keeps emitting the gravitons, okay? And I have, say, a coherent state of gravitons. A coherent state of gravitons is a curved spacetime. So in other words, if I study the path integral of the string theory with a lot of insertions of gravitons, I have a string propagating in curved spacetime. Okay, so we don't have, so often people will say, well, string theory is not background independent, but at least, what I am telling you here is that the string is background independent, at least in this, in this context when we are thinking about, string propagation in coherent backgrounds, which are due to emission of gravitons, right? And so, if that is the case, then if we have a political string, and the political string, just let me finish this in the later part. Suppose we have a political string, right? So our political string had a gauge-Weyl symmetry, right? But now I am saying that a string in curved spacetime is the same political string, except that it propagates with lots of insertions of graviton vertex operators, which we will discuss in more details exactly how it's going on. But if that is the case, what happens is that if your political string was Weyl invariant in flat spacetime, a political string must be Weyl invariant in curved spacetime. Okay, so must be Weyl invariant in curved spacetime. Okay. Again, just because a string propagating in a curved spacetime is the same Polyakov string, right? And we insist on whether the symmetry is a gauge symmetry, including all possible insertions. So now comes a very beautiful part, which we will not be able to talk today, but next time, is that you ask the question. So now suppose my string propagates in curved spacetime. What are the conditions that the theory is scale invariant? And what you will find out the Einstein equations. So Weyl invariance on the wall sheet, Weyl invariance on a string wall sheet again, kind of, we will compute the beta functions corresponding to wild transformations, right? So, and we want to require those beta functions to be 0 in order that our symmetry is anomaly free. So vanishing of these beta functions will produce for us Einstein equations in d dimensions. Okay? So while invariance on a string will shift will lead to Einstein gravity in d-dimensional space-time. Okay, so then I gave you a case why a Polyakov string is an interesting one. Because one of the predictions of the Polyakov string is that, and by Polyakov string I mean the one with local while invariance, is that it leads to Einstein gravity at long distances. So we do derive Einstein equations. We don't impose it by hand. And all the, with all the nonlinearities, all this stuff will come up automatically here. Now, in our case, I don't know what we will get. Definitely we will not get that because since while invariance is not a symmetry anymore, we don't insist that beta functions will vanish, so we will not have this beautiful relation to Einstein equations.
I just want to ask, in other words, by background independence, you actually mean that the curved spacetime is actually emergent as the coherent states of the gravitons emitted by the propagating strings?
That's what I mean, exactly. So what I'm saying is that, so here we are studying, you can think of it this way. So right now we're going to start scattering amplitudes, meaning that I prepare a state, okay? It's some excited state of the string. You can think of it as, say, graviton. And I scatter 2 gravitons into 2 gravitons in flat spacetime. And that will be described by a certain partition function, right, in a string. But what I can do, instead of doing 2 into 2, I look lots of gravitons simultaneously being scattered. And what will happen is that this scattering process of many gravitons, I can write down as a string propagating in curved spacetime. Okay? So a coherent state of graviton scattering in flat spacetime is the same. So the kind of the slogan, a coherent state of graviton scattering in flat spacetime is the same as propagating string in curved spacetime. Okay. So that's why, personally, I don't think, I don't think that background independence is such a big issue. Well, okay, you can say, look, what you are saying, you're saying that there is a background independence about, flat spacetime, right? Because I have to prepare a coherent state near the flat spacetime, which is true. But okay, I can go for hours about it, but that's what.
Well, this is a long debate.
Yeah, that's a long thing, but I'm just saying, I'm just explaining at least in which context you can think that the string theory is not something that you have to treat in a fixed background. Okay, because starting from now, suppose I prepare coherent scattering, right, or propagation of string in curved spacetime, I can still study a scattering, right? So the first step I will do, I will write down the curved background as a coherent state of lots of gravitons, and I just add a couple more gravitons to study. So the answers that I will get, I will interpret as a scattering of gravitons in curved spacetime.
But that background independence sounds like still on kind of perturbative level.
That's correct. Yeah, but the graviton itself is a perturbative object. That's why I'm saying we can go for circles forever. All right, guys. So good. So we're all now happy that we have to live with a Polyakov string. And we understand how crucial it is to have wild invariance. And so we now understand why it is important to have a string theory in 26 dimensions and nothing else. Okay, so now we will try to relate to physics. And we will try to understand how something that we do on a world ship is related to a spacetime. And so what we start discussing are the scattering amplitudes. And so I'm going to talk with some cartoons and just give you the general idea. So we're not going to go into specific computations today, right? But I'll just set up the problem. What I'm writing here is a critical space type, right? So RD plus 1. And then what I have, I want to look at the process, right? So I want to look at the process. So before what we discussed the string theory repetition function without any sources, right? So there was no string at the beginning and there was no string at the end. So if you wish, we looked at the vacuum amplitudes, right? But in order to get scattering, we have to talk about initial and final states, okay? And we want to have some kind of a space-time picture of it. Well, so the idea would be that now we have to look at the path integral with sources. So I have, you can think of that, I have two strings, right, specified at some very late time, t equals minus infinity. And then those strings propagate, right? And the propagation of a string is, as it propagates, they span a wall shape, right? And then the scattering, then they will scatter, right? And after that, they will propagate plus infinity. Okay? So I'm writing, if you wish, a sphere. What I draw here is a sphere with 4 long tubes. And each of these tubes corresponds to incoming string states, and 2 tubes correspond to outgoing. So this is supposed schematically to indicate the scattering process at which I have two initial states to 2 final states. Okay? And so what you would say, okay, so that's very easy. That's exactly the same how we do in quantum field theory. We just specify a boundary condition, right? So like in quantum mechanics, when we write down a path integral, we say that at time t equals 0, our x sits at x equals 0, then at time t equals 1, I have x1, and I sum over all possible trajectories with a fixed boundary condition. So you could ask the same question here. You can say, well, you specify those boundaries down here, boundaries up here, and what you have to do, you have to fill in these boundaries with a wall sheet, okay, with smooth wall sheets with all possible topologies, and then do exactly the same as we did before. Study the Polyakov path integral when you keep those guys fixed. And that would be a natural generalization to do, but you might have guessed that it will be impossibly complicated to do. Okay, so in other words, if I keep a well-defined boundaries at a very given specific point, then summing over all possible wall sheets is an unsolvable mathematical problem. Okay? I'm sure that there will be a huge prize if some of you guys will do it or develop techniques how to do it. That's also that's as valuable, maybe even more valuable, because then you will give job to other people, right? So then we must take we must look at some specific processes at which we have a chance to do the computation. And the point here is to go back to the infinite. We're going to look at infinite scattering rats. Okay, so what I'm doing here, I'm assuming that my incoming and outgoing states are connected to some non-trivial region by infinitely long loops. Okay, what does that buy us? Well, so let's go back and let's look at infinite cylinder, right? So if I have an infinite cylinder, and so here I have imaginary omega, right? So now omega is my bullshit coordinate on the cylinder, so if omega equals to 0, then I have U omega, imaginary omega, equals to minus infinity. So in some sense, by talking about infinite cylinders or infinite legs, what am I doing? I'm preparing my states at minus infinite time, right? And so what we know that if we have this infinite cylinder, we can use conformal map, right? E to the minus I omega. And so what will happen is that this infinite cylinder will turn into a disk, and there will be a hole cut out in the center of this disk. And the way how we cut out this hole will depend on exactly what state we prepare at t equals minus infinity. So we can do exactly the same thing with the scattering diagrams that I wrote there. So what you can do, since now we are looking at the scattering diagram which are connected by infinitely long cylinders, so the total map, of course, I cannot write it down for you. It's very difficult to do. But so here there will be its own local omega coordinate. There will be another local omega coordinate here. They, you know, for smooth world sheets, I can smoothly extend a coordinate omega along this leg to a coordinate omega hat in this leg. And so what I'm going to do, I'm just going to make a conformal transformation of this very complicated world sheet in such a way that I go from omega to z here, and from omega hat to z hat here. And again, for smooth world sheets, there will be a holomorphic, a smooth holomorphic interpolation between this coordinate and this coordinate. So if you look at this picture, what that map is doing for you, so it keeps, this is the outside, right? This is the top circle, right? So it keeps this guy fixed, but what it's doing, it shrinks the whole cylinder into the point. It fills in this hole, right? So what I can think of that scattering diagram, so I have some blob, right? So I cut out the holes. Okay, so this is my omega picture, right? Omega and all these local omega coordinates along the cylinders. So there are these holes which are cut out in the wall sheet where I attach my long legs. And now, after I did the Z transformation, what will happen is that those guys will get filled except with insertion of local operands. Okay? So after I go to the Z variable, then I will have, if you wish, a sphere, okay, so, with 4 local insertions on it, right? The insertions will be local. It will be just a local hole as long as the legs are infinitely long. Okay? Is that clear? Now, what that tells you, immediately what kind of questions you can ask in the strings here. For example, if you tell me you prepare 2 string states at time minus 1 second, and you want to know what will happen with a scattering of the string in 27 hours, I will not be able to answer this question because such a configuration I cannot represent by an infinite long legs. So in other words, the only question I can ask, if you prepare me a state at time t minus infinity, and I can tell you what is the outcome of that state at time t equal plus infinity. So in other words, because of this way of relating the problem of scattering, the only question you can ask in string theory are matrix, S matrix element, right? Okay, so right, so in this sense, a perturbative string theory is an S matrix theory. It's a theory of a scattering matrix, right? So is that clear? And actually, this is another thing where you can think about background independence, right? So I was telling you that I can think about string scattering in curved spacetime, but at the end of the day, since my computational ability restricts me to look only at the elements of the S matrix, which means that I must have a well-defined scattering state. So it means that at minus infinity and the plus infinity, I must have a flat spacetime. So a more precise statement is that there is a difficulty of generalizing the notion of S matrix, the way how we think about scattering processes in perturbative string, to backgrounds which are not asymptotically flat. So the string is background independent as long as you keep, the infinite past and infinite future to be asymptotically flat spacetimes. Then, the string theory, I would say background independent with, kind of fixed boundary conditions. All right, so very good. And so now what I said, it should be pretty obvious. What do we have to do here? Right, so this was omega, and this was that. So remember that when we do this exercise here, right, so we have a state that we prepare on an infinitely long cylinder. It was a state A. And so the map that goes to omega is just a map at which we have a local insertion of operator at the origin of the disk, right? So this map in which the cylinder shrinks to a point is the operator to state map. Okay? So so in other words, once we go here, so here we have different scattering states, right? And we can identify ingoing and outgoing states by simply saying, so here I have K mu, and so K1, K2 mu, K3 mu. Those are the four momenta in 46 dimensions, right, of my scattering state, right? I'm thinking that asymptotically I have d-dimensional Minkowski spacetime. And so we can identify ingoing or outgoing states by simply asking whether the zero component is positive or negative. So if the zero component is positive, so we have an incoming state. And if it is negative, it's outgoing. So if E is 0, so this is incoming. And when E is negative, we just have outgoing state. So now, once we go to the sphere, right? So what we will have, each of these, so here I have, in general, I have a state I, right? So in general, so then once I go to the Z plane, at each of at each point, I will have a local insertion of some operator, d sub I, right? D sub I at K sub I, right? So this is a vertex operator inserted on a wall sheet, right? Which corresponds to a scattering state I. Okay, so write it down. E sub I or K sub I is a vertex operator corresponding to a scattering state. So I have a scattering state I with d-dimensional momentum K sub I under this conformal map. Okay. So now, once you realize that, then you can write down immediately what's going to be the scattering amplitude, right? So if I want to evaluate the scattering amplitude, so I have I have states J1. I have a scattering of n strings, right? And so I put my string asymptotically in states J1 up to Jn, and each of these string states will carry momenta K1 up to Kn, right? So this scattering amplitude will simply be given by a path integral, right? So I still have exactly the same political path integral. I have to do sum over all possible wall sheets, right? Except that now my wall sheet must have holes, must have insertion of operator. So it's dx over times dg. So I still have to integrate over x field over the wall sheet metric. I have to divide by diffeomorphism, volume of diffeomorphism times volume of wire, right? And then I have a political action e to the minus sx minus lambda times the Euler character for wall sheet, right? So I have to take into account wall sheets of different topologies. And so now, now it becomes very clear that thinking about more complicated topology simply corresponds to thinking about quantum corrections to scattering amplitude. So the simplest topology, the one that we are talking so far, a sphere with insertion of local operators, it's like a tree-level scattering amplitude, right? And once I start including handles and so on, making a scattering process on a higher genus surface, that would correspond to quantum string loop corrections. Okay? And so what do I have to do here? Well, so here I have to insert vertex operators, right? I have to insert them on the wall sheet, but I want my answer to be diffeomorphism invariant. Remember, our guiding principle is to build up a theory which is diffeomorphism and while invariant on the wall sheet. So the only way I can make the scattering amplitude invariant under diffeomorphism is when I integrate over all possible insertions, right? So it shouldn't matter exactly where on the sphere I will insert the vertex operator. In other words, there is a symmetry. Think of it as a symmetry. When I consider scattering of strings, two strings come in, two strings come out. Exactly where they get attached to the sphere shouldn't matter. Okay. We want a scattering amplitude which is independent on these details. And what that implies that once I start inserting vertex operators, so I have to integrate over all possible insertions of these vertex operators. So that's for each I have an integral e to sigma I square root of gi, and then I have dj of k, kj, and sigma I. Okay. All right. I'm sorry, guys, if you cannot see. Okay. Should I rewrite it, or it's okay? It's okay. So all I'm saying is, so I'm inserting it. So I'm taking this dj kj, right, and I'm inserting it at the point sigma I. And all I have to do, I have to integrate over all possible insertion points. So I will have as many integrals as the number of insertions I have, and so I have to take a product with respect to j.
Okay. Here I have a question.
Yeah.
When these four insertions coincide, because it's possible.
Right, sure. Sure. So that's at the end of the day. We want to get an answer, right? And it's kind of similar that you have to do the same stuff as you do in quantum field theory. In order to get a finite answer, you have to regularize and renormalize. We will do some computations of the some explicit computation of the scattering amplitude. So you will see that yes, there will be a singularities, when the insertion will coincide. Yeah. But see, the problem is the way how you have to think of that is that that's a constant feature in quantum field theories, right? So you will get a singularity and you get the divergences in loop diagrams precisely when there is coincidence, right, of the type you are talking about. Now, in normal quantum field theory, we divide quantum field theory into renormalizable and non-renormalizable ones. The renormalizable ones are the ones in which we can make sense of, these coincident points, right? So we can subtract infinities. So the problem we faced in normal quantum field theories is that there is no way we can remove divergences when the two gravitons coincide. Okay, so when we study scattering of gravitons, a perturbative scattering of gravitons leads to non-renormalizable quantum field theory. And so that was one problem that actually led people to think, if you wish, about string theory. Okay, so what we will see is a graviton can be one of these states, right? It's one of the states of the strings that I'm preparing, and so I can put a string in a graviton state. And so the point is that these objects that I'm writing down, after you take appropriate regularization and renormalization, is well defined, and it's well defined for all states, including the scattering of gravitons. That's why people say that a string theory provides a consistent perturbative quantum field theory of gravity. Okay, by perturbative I mean, once I start talking about gravitons, I must talk about perturbative objects. All right, guys. So, let's see a couple more things that I want to mention here. Okay. So. Again, we want to insist on diffeomorphic invariance and Weyl invariance, and diffeomorphic invariance is already achieved, right? So what we did, we integrated with the right measure over the bullshit. But the thing that is left over is Weyl invariance, right? So which puts constraints, right? So which puts constraints as to the terms that we insert, the insertions that we do in our path integral must be Weyl invariant, okay? What I will show you next time is that it will come up automatically. So in other words, if I look at a particular state in a physical string spectrum, be it a tachyon or a graviton or some higher state, I can always ask the question, what is the local operator? So once I determine what is the local operator, I can compute what are the holomorphic and anti-holomorphic weights of this insertion. And I will find out that this guy is actually Weyl invariant, right? Because if you have a non-zero, so the holomorphic and anti-holomorphic weights will come to be zero, which means that that thing does not transform under Weyl transformations. And I'm saying that will come up automatically. All right, guys. So good. So one thing, let's see. So we're going to be kicked out today exactly at 1 o'clock because there is a talk. But let me tell you where I will start next time. Okay? So. Right. So if you look at this path integral, right? So there is again Hi's here. There is an Euler character of a bullshit. It's not, it's not something that we will worry about or will use. But I think that at some stage you have to learn about it, and this looks like a good thing to learn. So remember that this Euler character is related to a genus of a surface. It's related to the, if we talk about open strings, there can be boundary components. So the Euler character is given by that. And so exactly over what wall sheets I'm doing the summation there depends what kind of string theory I'm talking about. Is it oriented string or is it unoriented string? So next time, the first thing I will talk about is that you already mentioned this, that there is one thing that I was missing here, and that's a crosscut. Okay. So, and the Euler character, if I have an unoriented surfaces, there is a contribution coming from crosscaps. Now, I'm going to make an assumption that most of you haven't heard about a crosscap, okay? And so what I'm going to do, we're going to kind of take a slight detour, and I will explain you how you think about crosscaps. And so we'll think about Möbius straights and Klein bottle, and see exactly how we can visualize it. And that's we're not going to use it for anything unless you're going to go and study the second volume of Polchinski and try to. So there, when you talk about D-branes, you will end up talking about them. And so we'll see how we can think about those surfaces. And again, one of the arguments we're going to do that because those surfaces will show up in this path integral. All right, guys. So see you next week.
When will be our
last class? I don't know. I'm saying, what's the normal ending time for university?
This term ends in early April.
Okay, so let's make it so there is no class on April 10th, which is Friday, right? Because that's a Good Friday. So let's see. Okay, so April 17th. April 17th is well. Okay, I don't want to go so late. April 17th. So we're gonna make the last lecture on. But see, if I go April 3rd, that's too. I mean, we'll not make any. Okay, so let's don't answer this question. So it will be either April 3rd or April 17th. I'm not going to go past.
So another question is there another string